in this lecture I shall deal with the various factors which affect the intensities of the diffracted beams from a specimen. Say for example, if we look at the X-ray diffraction pattern from a powder camera, we find that there are large number of diffraction lines. Now, each line pair is due to diffraction from a particular HKL plane. Now, what we observe is that these line pairs, they are not of the same intensity. Some are very strong, some are reasonably strong, some are weak, some are very weak. Now, what is the reason for the difference in the intensities of the diffraction lines? So, in this lecture I am going to discuss those factors which affect the intensities of diffraction lines in a diffraction pattern. Now, there are various factors which play a role in determining the intensity of a diffraction line, and those have been written down here, namely polarization factor, atomic scattering factor, crystal structure factor, multiplicity factor, Lorentz factor, absorption factor and temperature factor. Now, I will discuss each of these factors separately. Now, we know that when we have an atom, or say the when you consider an electron in an atom, and if we allow a beam of X-rays to fall on this electron, if we allow a beam of X-rays to fall on this electron, then what will happen? This electron will act as a scattering center, and it will start scattering the radiation in all possible directions. So, this is what is known as the forward direction of scattering. Say for example, if we want to find out the intensity of the scattered radiation in a particular direction, say given by this, which makes an angle of theta with the forward direction, or I should let me write it as alpha, so that it does not confuse with the Bragg angle. Say we want to find out what is the intensity scattered in a particular direction, making an angle alpha with the forward direction. Now, this has already been given by Sir J. Thomson. So, he has given this relationship I equal to I0 e to the power 4 by r square m square c4 into sine square alpha. So, here I stands for intensity of the beam scattered by the electron in the direction alpha, I0 is the incident intensity, C is the velocity of light, alpha is the angle between the scattering direction and the direction of acceleration of the electron or the forward direction, E is the charge on the electron, m is the mass of the electron, and r is the distance from the electron where the intensity is measured. That means, r is this distance. So, according to J. J. Thomson, if an X-ray beam of intensity I0 is incident on an electron, then the intensity that will be scattered in a direction alpha with the forward direction at a distance r from the electron will be given by this expression. So, you see that the amount of X radiation, the intensity of X radiation scattered in different directions will be very different. And when it is in the forward direction, that means for the forward direction alpha is equal to 0. In the forward direction alpha is equal to 0. Now, the first factor which I am going to discuss is the polarization factor. Now, this factor arises simply because of the fact that the electric vector associated with an X-ray beam is not plane polarized. Say for example, we have an electron over here at the origin of this cube. Suppose a beam of X-rays is incident in this particular direction along the x direction. Now, the electrical vector associated with this beam of X-rays can be is E, which can be resolved into two components, E y along the y component and E z along the z component. Now, the intensity of the electric field component along y will be the square of E y, it will be E y square. The intensity of the z component of the electric field is equal to E z square. Now, since the electric field is unpolarized, that means it can be in any direction in the yz plane. Statistically, there is no reason why Ey and Ez will be different. So, we will take them to be equal. So, now we can write E square is equal to Ey square plus Ez square. Now, as I said, statistically Ey and Ez should be the same, because the electric field E is unpolarized. It can take any position along the in the yz plane. So, we can write Ey square is equal to Ez square, which is equal to half of E square. So, we know that intensity is the square of the amplitude. So, electric field amplitude, if it is E, we can write I0 is equal to E square. So, we can write I0 y, intensity of the field along the y direction is Ey square, and I0 z, the intensity of the electric field in the z direction is Ez square. Now, if we denote a point P in the xz plane, and if we want to find out the intensity of the radiation scattered by this electron at the point P, then we can find it out in this way. First, we find out how much is the scattered radiation from the y component of the field and how much is the scattered radiation due to the z component of the field, and then add them up. Now, this angle here, because this plane is perpendicular to this plane. So, this angle here is pi by 2 and this angle here is pi by 2 minus 2 theta, because after all what is the angle 2 theta? 2 theta is the angle between the incident direction and the scattered direction. So, this angle is pi by 2 minus 2 theta and this angle is pi by 2. So, the intensity at the point P due to the y component of the electric field I p y, according to Thomson's equation, we can write it down as equal to I o y, the intensity of the electric field in the y direction, e to the power 4 divided by r square m square c 4 into sine square pi by 2. So, this is equal to I 0 y e to the power 4 by r square m square c 4. Now, what will be the intensity of the scattered radiation by the electron at the point P due to the z component of the electric vector? It will be I o z into e to the power 4 by r square m square c 4 sine square pi by 2 minus 2 theta. So, it will be I o z e to the power 4 by r square m square c 4, the whole thing into cosine square 2 theta. So, the total intensity scattered by the electron at the point P in the x z plane will be equal to I p y plus I p z. So, if we add those two up, we come to this situation. It will be equal to I 0 e to the power 4 by r square m square c 4, the whole thing multiplied by 1 plus cosine square 2 theta divided by 2. So, in this equation we find, so far as the particular point is concerned, the only thing which is a variable is cosine square 2 theta. So, depending on the angle which the scattered radiation makes with the incident radiation, the value of the intensity will change. Now, this is a constant and these are all constant, and if we are talking about a point at a particular distance r, the only thing that is a variable is this part of the equation. Now, let us talk about the process of scattering of X-rays by an atom. An atom contains a large number of electrons, especially if we have a heavy metal like uranium. We know that there are 92 electrons. If we talk about hydrogen, it is only 1 electron per atom. So, the amount of X radiation scattered by an atom will depend on how many scattering centers are there in that atom. You see, the scattering of X radiation by an atom of a metal is such that the nucleus of the atom does not take part in the process. The nucleus of an atom is too heavy compared to the mass of an X-ray photon, and that is the reason why X-rays do not interact with the nucleus. So, X-rays will interact only with the extra nuclear electrons. So, one thing is very clear, that if we have an element with a higher atomic number that is supposed to scatter X radiation more than an element whose atomic number is lower. Now, let us see how to find out the amount of X radiation scattered by an atom with a number of electrons in it. So, we define a quantity, we call it the atomic scattering factor f, small f. It is equal to amplitude of the wave scattered by an atom divided by amplitude of the wave scattered by an electron. It should be written in the same direction. I would write in the same direction. So, small f or atomic scattering factor is the amplitude of X-ray wave scattered by an atom, scattered by all the electrons in the atom, divided by amplitude of the wave scattered by a single electron in the same direction. So, it is equal to, in case of only when the scattering is taking place in the forward direction. So, this is the forward direction, as you can see. This is an atom, these are the atomic shells. So, a beam of X-rays falls on it and it interacts with all the electrons. So, if we consider only the scattering taking place in the forward direction, then this is equal to Z, the atomic number, multiplied by AE. AE is the amplitude of X radiation scattered by a single electron divided by AE. So, F is equal to Z. So, this is true only when we talk about scattering in the forward direction. When it scatters in the forward direction only, it can be shown, it can be proved that the atomic scattering factor will be equal to the atomic number, that means the total number of electrons in the atom multiplied by the amplitude scattered by an electron, whole thing divided by the amplitude scattered by an electron. So, F becomes simply is equal to Z. So, if we consider a uranium atom, so when X with 92 extra nuclear electrons, then when an X-ray beam falls on those electrons and we consider scattering in the forward direction only, small f or atomic scattering factor is equal to 92. If on the other hand we have a hydrogen atom, then what will happen? Hydrogen has got one extra nuclear electron. Then if you have a beam of X-rays falling on an atom of hydrogen, so it will scatter radiation in the forward direction. So, for that hydrogen atom, F is simply going to be 1. So, please remember that when the atomic scattering factor is equal to the atomic number, we are talking about scattering in the forward direction only. Now, what about the value of atomic scattering factor when we are considering scattering in directions other than the forward direction? That is given by this plot. So, this is the plot of f versus sin theta by lambda. So, you see that this theta gives an idea of which direction we are measuring the scattered intensity, and lambda is the wavelength of X radiation. So, what we find, Z varies in this fashion, Z varies in this fashion, I am sorry, F varies in this fashion, and when theta is equal to 0, theta is equal to 0 means the forward direction, then what happens? We are over here. So, when theta is equal to 0, we are at this origin, and at this origin what is the value of F? It is equal to Z. So, you see that only for forward direction, if you consider the scattering, then atomic scattering factor of an element is equal to its atomic number, and when we consider scattering in any other direction, that means theta other than 0, you will find the atomic scattering factor is lower than in the case of scattering in the forward direction. We will now talk about another very important factor, and we call it the crystal structure factor. We call it the crystal structure factor and denote it by capital F. So, by definition, the crystal structure factor is equal to the amplitude of X-rays scattered by all the atoms in a unit cell of a material divided by the amplitude of X-rays scattered by a single electron. Say for example, this is a unit cell of a material, and say a beam of X-rays is incident in this direction, and the beam is designated by a unit vector S0 as we did previously, and say the scattering taking place in this direction. We are interested to find out what is the scattered intensity in this direction. This is denoted by, the scattered direction is denoted by the unit vector S. Say for example, we have got an atom here, we are talking about an atom here which is our origin, and an atom over there. So, we take this as the origin and say this is the jth atom in the unit cell. So, we are first considering an atom at the origin, this we have taken as the origin with fractional coordinates 0, 0, 0, and the jth atom whose fractional coordinates are uj, vj, wj. Now, we have already seen that when we calculate the scattered radiation from two different atoms, there is going to be a phase difference between the two, and that phase difference can be simply written as equal to 2 pi times s minus s0 by lambda dot rj, where rj is this vector connecting the origin to the point to the atom at x. So, this relationship we derived previously. So, this is the phase difference between the rays scattered by the atoms at this position and at this position. Again, we have seen that here if we take the s minus s0 by lambda as the vector sigma star hkl in the reciprocal lattice, we can write it simply as hs star plus kb star plus lc star, and rj is nothing but uja plus vjb plus wjc. A, B, C are the lattice parameters say in the real space. So, it will be equal to 2 pi huj plus kvj plus lwj. So, if we have two atoms, one at the position 0, 0, 0 in a unit cell and the other atom at the position uj, vj, wj, then the phase difference between the rays scattered by the two atoms will be equal to 2 pi times huj plus kvj plus lwj. Now, you see, whenever we are going to find out, when we are going to add up the scattered waves from a number of atoms in the unit cell, there should be a suitable method to add them up, because one thing is true, that when we talk about the scattered radiation, they have not only a magnitude, but they have a phase difference also. So, it is a kind of vector addition of waves that we have to do. Say for example, we have got say 3 waves, one given by A1, the second one given by A2, a third one given by A3. Say with respect to a particular wave A, A1 has got a phase difference with it by the amount phi 1, A2 has got a phase difference with it by the amount phi 2, A3 has a phase difference with it given by phi 3. So, how to add up the scattered radiations from all the atoms in the unit cell? So, every scattered wave can be resolved into two components, one along the real axis and the other along the imaginary axis. For example, if this vector makes an angle phi with the real axis, then we can write down this vector as A cosine phi plus I A sin phi. So, this quantity can be written either as A e to the power I phi, or we can write it as A exponential I phi. So, now what will be the amplitude of X-ray scattered by the jth atom? We know that if F is the atomic scattering factor, small f is the atomic scattering factor. So, in this case Fj is the atomic scattering factor of the jth atom. So, if we multiply it by Ae, the amplitude scattered by a single electron, what it gives? Because Fj, the atomic scattering factor, is nothing but the amplitude scattered by the jth atom divided by Ae. You see, Fj, the atomic scattering factor of the jth atom, is nothing but the amplitude scattered by the jth atom divided by Ae, amplitude scattered by a single electron. So, if we multiply this with Ae, that means it will give us the total amplitude scattered by the jth atom. So, in this equation, this is the total magnitude of the the total amplitude scattered by the jth atom is Fj multiplied by Ae, and this is the phase term. So, when we write down the total amplitude scattered by the jth atom, which will give you the value of the amplitude, the magnitude of the amplitude and the phase term, it will be Fj Ae multiplied by exponential 2 pi I into Huj plus Kvj plus Lwj. So, this is the total amplitude scattered by the jth atom in the unit cell. Now, what will be the total amplitude which is scattered by all the atoms in the unit cell? So, this expression, we take the summation of this over all the j atoms in the unit cell. So, knowing the amplitude scattered by the jth atom as this, we can easily find out what is the total amplitude scattered by all the atoms in the unit cell simply by having a summation of this quantity taken over all the j atoms. So, what will be the crystal structure factor F for the unit cell? Now, here is a mistake, it is written in the reverse way. So, crystal structure factor will be A divided by A. Please note that there has been a mistake here. So, crystal structure factor will be A divided by A, where A stands for the total amplitude scattered by all the atoms in the unit cell divided by the amplitude scattered by a single electron. So, this is A. So, we divide it by Ae. So, what will happen? A will cross out. So, we will have this expression for the crystal structure factor. So, the crystal structure factor of a unit cell of a material will be equal to Fj exponential 2 pi I Huj plus Kvj plus Lwj with summation taken over all the J atoms in the unit cell. We will apply this concept of crystal structure factor in some particular cases to illustrate how important this factor is. Say we talk about 3 Bravais lattices belonging to the cubic system. One is the simple cubic, the other is the face centered cubic or FCC, and the third one is the body centered cubic or BCC. Now, you will remember that in simple cubic 8 corner atoms, their total contribution to this particular unit cell is 1 atom. Here there are 8 corner atoms and 6 face centered atoms. So, their total contribution to this particular unit cell is 4 atoms, and in the body centered cubic the total contribution of the 8 corner atoms and 1 body centered atom is just 2 atoms, so far as this particular unit cell is concerned. So, the 1 atom in the simple cubic system, its fractional coordinates are 0 0 0, and the 4 atoms in the FCC unit cell have the fractional coordinates 0 0 0, half half 0, half 0 half and 0 half half. And in the body centered cubic material, the 2 atoms have the fractional coordinates 0 0 0 and half half half. Now, let us talk about the simple cubic system. How many atoms are there per unit cell? There is only 1 atom at the origin 0 0 0. So, we have to take summation over only 1 atom at 0 0 0. So, for simple cubic, capital F is equal to small f exponential 2 pi I h into 0 plus k into 0 plus L into 0. So, how much it is? Small f exponential I into 0. So, it is equal to 1. So, it will be simply f. So, simple cubic system is one in which the crystal structure factor is simply equal to the atomic scattering factor. So, in the simple cubic system, we find that capital F, the crystal structure factor, is simply equal to the atomic scattering factor, assuming that in the unit cell all atoms are of the same kind. Now, what does it say? Here we do not have any expression containing H, K or L. That means, a simple cubic system crystal structure factor is independent of HKL. That means, you see, when you look at the amplitude, the crystal structure factor, it is the amplitude of X radiation scattered by all the atoms in the unit cell divided by the amplitude scattered by a single electron. That means, in the when you consider the intensity of a diffraction line, it is actually square of the amplitude. So, f square appears, it is proportional to f square, the intensity is proportional to f square. So, you see that f is a very important term indeed, and what it says in simple cubic, it simply does not matter what are the HKL planes, f is always a positive quantity. You see, small f is always a positive quantity. Okay? Small f is the atomic scattering factor, and atoms will scatter depending on their atomic scattering factor. So, there will be some intensity, there will be diffraction possible from every HKL plane that is present in the material. Now, let us go to the case of FCC, the face centered cubic system. Now, in FCC, we know that there are 4 atoms per unit cell, and they are located at the fractional coordinates 0 0 0, half half 0, 0 half half and half 0 half. So, you see that when we calculate capital F, it has to be calculated over 4 atoms, because in the unit cell there are 4 atoms. So, we write down all those 4 terms F exponential 2 pi I h into 0 plus k into 0 plus L into 0 plus exponential 2 pi I h into half k into half plus L into 0 exponential 2 pi I h into half k into 0 L into half and exponential 2 pi I h into 0 plus k into half plus L into half. So, that gives us equal to small f exponential 2 pi I into 0 plus exponential pi I h plus k exponential pi I h plus L exponential pi I k plus L. So, we have, since this term is equal to 1, exponential 2 pi I into 0 is 1. So, it is small f into 4 terms 1 plus exponential pi I h plus k exponential pi I h plus L exponential pi I k plus L. Now, if we examine this expression very, very carefully, there can be some different possibilities. Say for example, if we have a situation where h, k, L are mixed quantities, that means some are odd, some are even, then what happens? If h, k, L are mixed quantities, say 2 of them are odd, 1 of them is even, this is a possibility, or 2 of them even, 1 of them an odd quantity. So, if that be the case, what will happen to the values of h plus k, k plus L and L plus h? Say if it is this, the 2 are odd, 1 is even, that means say for example h, k, L, we have h is equal to 2, k is equal to 4, 2 odd. So, in this case I am sorry. So, in this case let us say that h is equal to 1, k is equal to 3, L is equal to 2. So, 2 odd and 1 even. So, what happens to these values? H plus k is 4, k plus L is equal to 3, L plus h is equal to 3. So, we find 1 is an even quantity, 2 are odd. Now, let us look at the other possibility, that out of h, k, L, 2 are even, say h is equal to 2 and 1 odd, say k is equal to 1 and L is equal to 4. Then what happens to these values? H plus k will give us a value of 3, then k plus L will give us a value of 5, L plus h will give us a value of 6. So, here 2 are odd, 1 even, and in this case also 2 are odd, 1 is even. So, in this expression, out of the 3 quantities h plus k, h plus L, k plus L, say this is even, this is even, this is I am sorry, this is odd, this is odd, this is even. So, 2 will be having odd values and 1 will be even value. Now, we all know that exponential when we talk about exponential, pi I into n, when n is an odd quantity, when n is odd, this value is equal to 0. On the other hand, exponential pi I into n, when n is an even quantity, it is equal to 1. So, what will happen here? Here, out of these 3 expressions, 2 will be minus 1. I am sorry, it was a mistake I made here. I want to correct it. So, if it is odd quantity, this has got a value minus 1, and if it is an even quantity, it has got a value of plus 1. So, what will happen in these 3 expressions here? 2 will be minus 1, 1 will be plus 1. So, if we add them up, it will be small f 1 minus 1 minus 1 plus 1, that means f into 0. So, it will be simply 0. So, you say that if we have a situation where H, K, L are mixed quantities, then the value of f will be equal to 0 in case of FCC material. So, if we have an FCC material, then capital F will become 0 when H, K, L are mixed quantities. Now, what is the other possibility? That H, K, L are unmixed quantities. So, let us take a case where H, K, L are unmixed. That means either all odd or all even. So, now let us think about the possibility where H, K, L are unmixed, which means all 3 of them are odd quantities or all 3 of them are even quantities. So, when all 3 of them are odd quantities, let us have H is equal to say 1, K is equal to 3, L is equal to 5, all odd quantities. So, what happens to H plus K? It is an even quantity. K plus L, that is also an even quantity. L plus H, that is also an even quantity. So, in that case, we find that all these H plus K, H plus L, K plus L is an even quantity. Now, and if all the 3 are even, then of course, H, K, L, H plus K plus L plus H, all are even quantity. And if these are even quantities, their values are 1, 1 and 1. So, we see that when H, K, L are unmixed quantities, whether all of them are odd or all of them are even, the 3 terms in this expression, each one of them becomes equal to 1. So, as a result, capital F becomes small f multiplied by 4. So, here f becomes equal to 4 times small f when H, K, L are unmixed quantities. So, you see the implication of these results. In case of simple cubic, f is independent of H, K, L. So, since small f is always a positive quantity, because every atom will scatter, then every atomic plane will be able to scatter the radiation. What about FCC? We find there will be no scattering when H, K, L are mixed quantities. You see, now we are talking about a unit cell. So, all the atoms of the unit cell will scatter, and this is the situation where the scattering will be totally destructive, and the total scattered intensity will simply be equal to 0 when we have HKL mixed. So, if you take a diffraction pattern of an FCC material, HKL mixed, those planes will not give rise to any diffraction. On the other hand, if you have HKL unmixed, that means atomic planes for which the HKL values are unmixed quantities, there will be diffraction because capital F is equal to 4F, which is a positive quantity, and the intensity is square of F like that. So, we see that compared to a simple cubic and comparing simple cubic and FCC, simple cubic material will show more number of diffraction lines because all the HKL planes of different types can diffract, but here the number of diffraction lines will be less because those planes for which HKL are mixed, they won't be able to diffract. Now, we will go to the BCC case, the body centered cubic unit cell. So, in the body centered cubic unit cell, we know that there are 2 atoms per unit cell, one located at the fractional coordinate 0, 0, 0, the other located at half, half, half position. So, the summation here has to be taken over 2 atoms only. So, it will be exponential 2 pi I h into 0 plus k into 0 plus L into 0 plus exponential 2 pi I h into half plus k into half plus L into half. So, it will be equal to small f into 1 plus exponential pi I h plus k plus L. Now, here again we can have 2 different possibilities. Say if h plus k plus L is equal to odd, that is one possibility, h plus k plus L is equal to even, that is the other possibility. Now, if h plus k plus L is odd, then exponential pi I into h plus k plus L, its value will be minus 1, and when h plus k plus L is equal to even, the value of this quantity will be plus 1. So, you say that here f will be equal to 0 when h plus k plus L is equal to an odd quantity. When it is odd quantity, this expression has got the value of minus 1. So, capital F will be small f into 1 minus 1 is equal to 0. Now, how much will be f when h plus k plus L is an even quantity? It will be 1 plus 1. So, it will be 2f when h plus k plus L is equal to an even quantity. So, you see that depending on the Bravais lattice and the location of the atoms, we can have a positive atomic crystal structure factor in case of the simple cubic system for all atomic planes, and we are, as we have already said, that when we talk about the intensity, intensity is always proportional to the square of the amplitude of the X radiation, which will be scattered by all the atoms in the unit cell. So, in simple cubic system, all the atomic planes will be able to diffract. In case of FCC, only those atomic planes for which HKL are unmixed will be able to diffract, and in case of BCC materials, only in those cases where H plus K plus L is an even quantity will be able to diffract.